there's actually when it comes to the side lengths, there's actually a relationship between them. It's not just they're going to be different sizes. Those sides are actually going to be proportional to each other, which we'll talk about what that means in just a second. So go ahead and open up your packet to the first page. So, just like I just said, dilation produces another shape that has side lengths that are scaled by the same factor, and the angle measures are the same as the pre-image. All right. So when we did dilations, we were usually given a scale factor. That's what we would multiply to all the sides of the original to get the new sides. All right. Now, again, two figures that share characteristics that have the same shape but different sizes, that's known as similar figures. Now, two geometric figures called similar. First off, this is the symbol for it. So just how an equal sign with a squiggle on top means congruent, if you just see a squiggle and no equal, that means similar. All right, so squiggle with an equal sign under it's congruent. If you just see the squiggle, it's similar. All right, you need to know that notation. Now, all pairs of corresponding sides are proportional, meaning that they have been scaled by the same scale factor. So in other words, if we divided each set of corresponding side lengths, you would get the same number, all right, when you divide those two sides. Now, on the other side, all corresponding pairs of angles have equal measures. So this is a callback to, do you guys remember when we were doing all the congruency postulates, and when I told you that one of the ones that does not prove congruence is angle, angle, angle? That's why. Because angle, angle, angle can show similarity, but it cannot show congruence because the side lengths can clearly be changed. All right. Now, it says for this first one to use tracing paper. We're not going to do that. The angles are in fact congruent. All right. So let's mark the corresponding angles. So it says that ABC is similar to DEF. Remember, sometimes the way they name the triangle, that shows you which letter corresponds with the other letter. All right, so someone raise your hand and tell me one set of corresponding angles. Rajan. That's sides. I'm talking angles. Ephraim. So CBA and FED, so these two angles. What's another set? EDF. I want to do this with a different color. Oops. So EDF and BAC, which means our last set is BCA and EFD. Now, I'm marking them congruent because they are, in fact, congruent. All right. Now, it wants us to determine the lengths of the missing sides of both triangles and show how you found your values. So, let's think about this in terms of a dilation. It's clear that if we started with this picture as our pre-image and dilated it by some scale factor, we get this image. All right. Who remembers how you find the scale factor? What is one way that I can find the scale factor? So let me ask you this. Are there any corresponding sides on these figures that have a side length on them? All right, what is it? 14 and 7. All right. So these two sides right here, they're corresponding sides, and they both have a side length. How can I use that to my advantage to find the others? You divide 14 by 7. So if I divide 14 by 7, what will my scale factor be? 2. So 2 is my scale factor. So the two sides I need to find are EF and AC. So how would I find EF? Right. EF, BC is its corresponding side, which is 8. So all I got to do is, because that's the smaller one, we're going to the bigger one, I just multiply 8 times 2. So that's 16. So EF is 16. How do I get AC? Someone beside who has not talked yet today. So someone who has not talked yet. So how do I get AC? It's a similar way that we just got EF. So for we don't multiply 20 by 2 because we're going from big to small. So we divide it. Good. So we're going to divide 20 by 2. That'll give us 10. Now, another way you could have found this, so this is just another way, which I do recommend writing down, is you could have set up proportions because the sides are proportional. So we could have done 14 over 7 is equal to, let's say we're finding AC. So you got to put the correct side with the correct triangle, all right? So where would AC go in this proportion, on the top or the bottom? It's on the bottom because we want to be next to the 7, all right? Because they're on the same triangle. And then we would put 20 on top because 20 goes with the 14 because they're on the same triangle. And then we get to do what you guys always want to do when you get fractions and cross multiply. So 20 times 7 is 140, and that's equal to 14 AC. So how do I get AC by itself? Divide both sides by 14. Is it not true that 140 divided by 14 is 10? Yes, it is. So that's the other way you could have gotten it. You could have set up proportions. So it says, give a dilation of triangle ABC that will produce an image of A prime, B prime, C prime that is congruent to DEF. And how do we know it's congruent? Yes. Yeah. So we already found the scale factor. So we can go ahead and write this dilation. So triangle A prime, B prime, C prime is equal to 2 times triangle ABC. I'm going to put that in parentheses. Now, why did I multiply ABC by 2? Why does that give us this dilation? That will be congruent to DEF. Why did I multiply by 2? What do we typically do with dilations?
We typically we change their size somehow.
So we change the sides lengths by doing what? Multiplying the scale factor. All right. So it's congruent. So A prime, B prime, C prime is congruent to triangle DEF because the scale factor from triangle ABC to triangle DEF is 2. So when we deal with similarity, it's just dilations, okay? So it's a lot of, when we're going to be dealing with similar triangles, it's going to be a lot of proportions. So get really good at setting up those proportions, and then you just be doing some cross multiplying. All right. So it's not terrible. Now, we can formally define two similar figures in a manner that is similar to how we define two figures as congruent. So, two geometric figures are similar if there exists a similarity transformation that will map one figure onto the other. So, this is either a dilation alone or a sequence containing a dilation in a combination with a rigid motion. So, remember when we did composite transformations, and sometimes we would have, like, say, a translation, then a rotation, then a dilation. As long as a dilation is part of its sequence, it creates similar figures. All right, so just know that if dilation's in there somewhere, it's similar. Now, this next one states that ABC is similar to DEF. And we're going to describe a similarity transformation that will map ABC onto DEF, just to kind of help us visualize. So, first off, let's say we start with AB. All right. Now, they mark the angles for us. Okay. So remember, tick marks show you the corresponding parts. All right. So that means A goes with D, B goes with E, C goes with F. What do you think? What's one thing that you think happened to go from A to go from this triangle to this triangle? What's one thing that you think happened? Transformation-wise. So did a reflection happen? Did a rotation happen? Did a translation happen? Did a dilation happen? What do you think, Carrie? Say one more time. It does look like a reflection, but be careful because look at where the corresponding angles are. So I wouldn't necessarily say reflection because of where the corresponding angles are. But that is a good thought. John, what do you think? I would think more on the lines of a rotation happened. So I would say a rotation happened, and it looks like it would be 90 degrees clockwise. All right. So I think it rotated 90 degrees clockwise. Then, what do you think happened? Someone else. So once we rotated it, it would look something like this. So if we rotated it, here's what it'll look like. So here's A, C, and B. Now I drew it smaller than it actually is, but you guys get the gist. Okay. Now it's not quite on top of DEF yet. So what else do you think happens? Carolina. It dilated. All right. So we can say it dilated by some scale factor. We don't know what that is, and that's okay if we don't, because they don't give us enough information to find that. But we know it at least dilated. So if I redrew the figure, still looks like this, just slightly bigger. So that's B, A, C. And there's one more thing that had to happen. You had to have a translation of some sort. Whether that B goes up a little bit, down some, to the right some, to the left some, whatever. So once we do that, then it would transfer onto DEF. Now, why are we doing this? Well, first off, it's good review from Unit 1. All right, it's good connection to the two. But also, it shows that even though the orientation is different, they can still be similar figures. All right, so just like how orientation with congruent figures doesn't matter, orientation with similar figures doesn't matter either. So, we're going to skip exercise 3 because it's pretty much more of the same and go to exercise 4. So, exercise 4 states triangle ABC is similar to triangle DEF. So, those two triangles right there are similar to each other. Now, we need to figure out the scale factor that would be needed to dilate ABC so that the image is congruent to DEF. So, a couple of ways we can do this. Who remembers how you find the scale factor? Michael, just put it on my desk. Who remembers how to find the scale factor used to dilate an image onto another one? So especially if it's on a coordinate grid. Who remembers how I do that? Well, we just did it in example 1, kind of. So what do you think I'm going to do? Chris, just put it on my desk. So, example 1, how did we find the scale factor from example 1? So you found corresponding sides and then you divided them. So the new by the old. So what do you think I'm going to do here? Find corresponding sides for 1. But then, how would I figure out the scale factor? I need to get some side lengths, or I can use points. It doesn't really matter. I would say more on side lengths because we can actually get some nice side lengths. Come on, guys. There are 2 sides on each of those triangles that I can easily find the side lengths to. Which 2 sides? So BC I can find easily because it's a vertical line. I can just count units. Same thing with EF. So I'm going to do that. So if I count how many units BC is, it's 1, 2, 3, 4, 5, 6, 7, 8. So BC is 8 units long. EF, because its corresponding side, is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units long. What's the other set of sides that I can easily find side lengths to? AB and ED. So AB is 1, 2, 3, 4. ED is 1, 2, 3, 4, 5, 6. Now, I don't really care about the side lengths of AC and DF because right now I have enough information to check for the scale factor and to check similarity. All right. So, how do you think I can find the scale factor? Using those sides. Are you done? Division. So I need to divide the new image by the old. All right. So you always use the corresponding sides. So I'm going to use ED and AB. So I'm going to do 6 divided by 4, which that simplifies down to what? Not 2 over 3, but 3 over 2. Now, to check, because remember, they should all be by the same scale factor. I'm going to do the same thing with the 8 and the 12 just to check myself. So I'm going to do 12 divided by 8. Does that simplify down to 3 over 2? Yes or no? Yeah, it does. If you divide both these by 4, 12 divided by 4 is 3. 8 divided by 4 is 2. So my scale factor is 3/2. Now, we're not going to do part B because I don't really care about the transformation sequences. The biggest thing that I'm more worried about is, can you get the scale factor? All right, that's what you need for similarity. You need to know how to get that scale factor. Now, this last exercise. All right. Points B and D lie on AC and AE such that BD is parallel to CE. So they're saying that these two are parallel to each other. Now, it's not mid-segment theorem because if you look, these are clearly not on the midpoints. Point D is not on the midpoint of AE and point B is not on the midpoint of AC. All right. So we can't really use mid-segment theorem. However, we could figure out some stuff. All right. So, if I want to do a dilation of ABD, so this triangle right here, onto BCE. So this is a triangle within another triangle. They're still going to be similar to each other, but be careful with those. It's a triangle within another triangle. So they're not separated like we're used to. Now, how would I give that dilation? Well, I would say that we would dilate ABD by some scale factor. Let's call that X. About, what is the only point on both triangles that they share? A. So that would actually be the point of dilation because they're connected. All right. So since they share point A, that's going to be the point that they're going to dilate. So like we're used to dilations being about the origin. All right. This will be about point A. Now, that's all great and all, but I'm more worried about part B. So it says which proportion is incorrect based off of the fact that those two triangles are similar. So, first off, if we're talking angles, A is obviously going to be congruent to itself because of what property? Why is A congruent to itself? Reflexive. It's in the exact same spot. Now, angle B and angle C are congruent to each other. Why do you think they're congruent to each other? It's not just because they're corresponding, but why can we for a fact say that those two angles are congruent to each other? What's true about these two lines? They're parallel. Could I not say if I extended these lines that this side could be a transversal? Yeah. So what's the relationship between these two angles? I'll give you a hint. Those angles are what to each other? They're congruent, but think about what we would call them. Not vertical. Corresponding. Good. So these two angles are congruent because corresponding angles and parallel lines are congruent. All right. So they're congruent because they're corresponding. Same thing over here. These two angles are congruent because corresponding angles on parallel lines are congruent. And again, this one is congruent to itself because it's reflexive. Now, let's check all of these proportions and make sure they're correct. All right, so when it comes to proportions, the sides got to match up. All right, so in other words, if the proportion should have either the old, new, new, old, or it'll be like from the same triangle. So 2 from the old and then the corresponding from the new. All right. So let's look at this first proportion. So they said AC over AB. So first off, is AC and AB corresponding to each other on this triangle? So we have AC, which is here, and AB, which is here. Or, sorry, I said that backwards. AC is the purple, AB is the red. Are they corresponding sides? Yes. So now we got to make sure that those sides match up. So CE, so right here, and BD, are those corresponding sides? Yes. So first off, we know that they come from the same that they're the corresponding sides. Do they also match up? So is AC and CE on the same triangle? Yes. Is AB and BD on the same triangle? Yes. So that proportion's correct. Now, this next proportion, angle A and angle A, it's obviously on the two triangles, so we know that those two match up. But angle ABD, so ABD is this purple angle right here. And angle ACE is this purple angle right here. Do those two match up? Yeah. So that proportion's correct. Then we have AD over AE. So AD over AE are those two corresponding sides. Yeah. Then we have AC over AB. Are those two corresponding sides? Yes. But now let's look across. Is AD and AC on the exact same triangle? No, they're not. AD is on the smaller triangle, AC is on the bigger triangle. So since these parts right here don't match up because they're not on the same triangle, this is the proportion that's wrong. And then these are just the sets of the corresponding angles, and they are true. So, but you gotta be careful. Everything, when you make your proportions, everything has to match up. Yes, ma'am. Write your name on the board, and then whenever you get back. Actually, everyone is back. Where's my, no, just go. All right. Now, we're not quite done with notes yet because now we got to talk about what makes similar triangles so special. So go to page, I believe it's page 5. Should say 2.7. Now, this one's pretty quick because it's just more of the same, but we are also going to learn about the postulates that we can find similar triangles from. So, just to recap, similar figures will have congruent corresponding angles and corresponding sides that are proportional. All right. Just remember that if two geometries are similar, it's the dilation of one figure to make it congruent to the other figure. Now, we're going to skip part 1, all right, because that's just more of what we did in the previous section. We're going to move on to the newer stuff. So, that newer stuff is our similarity postulates. So, the first postulate is one of the ones that I said that you can use to not show congruency, which is angle criterion. So, you see that as AA. You can also see it as angle. It doesn't matter. So if it's a double A or a triple A, it's pretty much the exact same thing. Because remember, double A, it's implying that the third angle is congruent by the third angle theorem. All right. So in the diagram, we're going to explain how angle criterion for similarity allows us to conclude that these two triangles are similar. They also state that those two lines are parallel. So QR and NP are parallel. And we're going to show that we have the angle criterion. So between these two triangles, and again, I'm talking about this tiny triangle and this big triangle. Can someone tell me between those two triangles, what is one definite congruent angle that we can 100% say is congruent? So it's one angle on these two triangles that is 100% congruent that we know for a fact. Jared, say one more time. Did you say M? N? Not N. Well, if it was N, what's its congruent partner? Yeah. So N and Q are technically congruent. Why? We just said it in the previous section. So there's two lines that are parallel, and look at where they are. Rajan. They're corresponding. So it's true because corresponding angles in parallel lines are congruent. What's another set of congruent angles? Someone who has not talked yet today. So it's another set of congruent angles that we can for a fact say is congruent. Come on, guys. What'd you say? R and P. Good. And why are those two congruent? So angle P is congruent to angle R. Why? What are those two angles? What's the relationship? They're on parallel lines again. They're corresponding. And there's one more angle that I can say for a fact it's 100% congruent. Which one? Not M and Q. just M. M can be congruent to itself. Because if you look, M is an angle that's in both triangles. It's the top angle for the small yellow triangle, and it's the top angle for the bigger green triangle. They share that angle because it's a triangle built into another triangle. So angle M is congruent to itself. Why? What's the property that lets us do that? Nope. What's the property that lets us say that something is congruent to itself? Reflexive. Good. So that's kind of like a very, wasn't necessarily a proof, but there were proof-like features in there. All right. We gave a statement, and then we told us the reason. But we weren't necessarily proving anything. We were just trying to show that all three angles were congruent. Now, because of that, we can for a fact say that triangle MQR is similar to triangle MNP by the angle-angle theorem. Because we have two or all three angles that are congruent. Now, since they're similar, we can now use some side lengths and calculate some sides using the similar properties. So they said that MQ, which is this segment right here, is 8. They said NQ, which is this baby segment right here, is 6. And NP, which is this big segment right here, is 21. And they want us to find the length of QR, so I'm going to call that X. Now, I need to set up some proportions. That's going to be the easiest way to find it. So, how can I set up my proportion? So how can I set up the proportion that has the two sides already marked, the two corresponding sides already marked? So are there two sides that are marked and are known? There is. Which sides? MQ is one side, but QN is technically not its corresponding side. The corresponding side would be MN. However, do we not have enough information to find MN? We do. Because if you look, we got pieces of that segment. We got the first piece, which is 8, the second piece, which is 6. And we just add those together to get MN. Yeah. So what's actually the length of MN? 14. So the length of the whole side is 14. So be careful with those because they will throw those at you. All right. They may give you enough information to find the side, but they don't outright say what the side length is. You just have to add them together. So how would I set up my proportion? Using those two side lengths. So I'm going to be using 8 and 14 because those are my two side lengths and corresponding sides. So how would I set it up? Blank over blank. What should I do? You can do 14 over 8. You could have also done 8 over 14. It doesn't matter. All right? It doesn't matter how you set up that first proportion. What matters is how you set up the second proportion. So I'm going to leave it as 14 over 8. Now, the other two corresponding sides is the X and the 21. Now, this is where it matters. Because remember, now we got to match up the triangle to the triangle. So, what should be in my numerator? What value, 21 or X? So what value? So, in other words, whatever value we pick should come from the same triangle as 14. 21. Because 14 and 21 are on the exact same triangle. That's what I mean by it matters. You got to make sure the two triangles match up. So that means 8 would go with x, because 8 and x are on the same proportion. Now, how can I solve for x? What did I say you can do with this? Just cross multiply. Butterfly method, whatever you want to call it. All right. So I got 14x is equal to 8 times 21. Well, what's 8 times 21? It's what? 168. So I have 168 is equal to 14x. So how do I solve for x? What's my last step here? Divide both sides by 14. So x will be equal to what? 12. So that is the length of QR. So this right here is 12. All right, so that's how you solve for missing sides. You set up the two proportions, cross multiply, and then solve that linear equation, which typically you just end up having to divide by something. Now, the other two ways we can prove similar triangles. The side criterion for similarity. That's SSS. Now, not to be confused with side for congruent triangles. So side for congruent triangles means all three sides are congruent to its corresponding pair. But side for similar triangles means that all three pairs of corresponding sides are proportional, meaning they're the same value when you set up the proportion and simplify them. All right. So that's the difference between side for similarity and side for congruence. Congruence, all the sides are congruent. Similarity, all the sides are proportional. The other one is side criterion, so SAS. And again, not to be confused with SAS for congruency. So two of the sides have to be proportional to two of the sides on the other triangle. And their included angles, which remember, that is the angle between the two sides. That included angle has to be congruent in order for those two triangles to be similar. So the angles still has to be congruent. So the angle part of SAS still has to be congruent, but the side parts have to be proportional. So let's look at these examples. So we are going to basically show that this first set of two triangles, so ABC and DEF, are similar by side. So we have to check that every set of corresponding sides are proportional. All right. So first off, what's my first set of corresponding sides? What is one set of corresponding sides? Tell me the names of them. CB and FE. So I'm going to check, because we want to divide. It doesn't really matter which one you divide it by, but I'm going to do the bigger one divided by the smaller. So I'm going to do FE divided by CB. So I'm just going to replace that with their side lengths. So 8 divided by 4. What's 8 divided by 4? 2. So that means that for every other pair of corresponding sides, when we divide their two sides, we should get 2. Now, Since I did the bigger over the smaller as my proportion, I need to make sure I set up my other two proportions the exact same way. Otherwise, it will appear that you don't have the same scale factor. So that's what's important with these. You got to be consistent with how you set up those proportions. So someone else, name me another set of corresponding sides. AC and DF. So DF is the bigger one, so I'm putting that one on top. AC is the smaller one, so I'm putting that one on the bottom. So I got 6 divided by 3. What's 6 divided by 3? 2. All right, so far so good. But just because 2 sides are proportional doesn't automatically mean the third side's proportional. You gotta check all 3. So what's my last set of corresponding sides? Someone who's not talked yet? AB and DE. So I'm gonna put DE first, because that's my bigger one, over AB. So that'll be 10 over 5. And again, if you flip those fractions, like you did the smaller over the bigger, you would just get 1/2 instead of 2, which it doesn't matter. It's still going to give you the same proportion. Because what's 10 divided by 5? 2. So since all 3 sides are proportional to each other, meaning they have the same scale factor, we can say that triangle ABC is similar to triangle DEF by side, side, side. All right. Now let's look at the side angle side example. So first off, are the 2 angles that they gave us congruent? Yes. So these 2 angles are congruent. So we can say angle ABC is congruent to angle DEF. All right, so that's our first criteria. Then I need to check the proportional sides. Now, before I even check the sides, I need to make sure that angle is between the 2 sides that they gave us. So, is that angle for both triangles between the 2 given sides? In other words, those 2 sides make up that angle. Yes or no? Yeah. Because if you look at it, 15 and 21 make up this angle, 10 and 14 make up that angle. All right? They actually physically form the angle. That's how you can tell if it's side angle side. The 2 given sides should physically form the congruent angle. So, what's one set of corresponding sides? A, B, and DE. So I'm going to do DE over AB. Again, you could do AB over DE. It doesn't matter as long as you keep it consistent between both your proportions. So I'm going to do 15 divided by 10, which 15 over 10 will simplify down to what fraction? It'll be 3 over 2. So if you divide both 15 and 10 by 5, 15 divided by 5 is 3, 10 divided by 5 is 2. Now, what about my last set of corresponding sides? First off, what are they? EF and BC. So I'm going to do EF, because I did DE first on the previous one, over BC. So that'll be 21 over 14. So if I simplify that fraction, will I still get 3/2? Yeah. You can divide 21 and 14 by 7. 21 divided by 7 is 3. 14 divided by 7 is 2. So we got 2 proportional sides and an included congruent angle. Thus, we can conclude that triangle ABC is similar to triangle DEF by side angle side. Any questions? So, unlike congruency where there's 5 postulates, there's only 3 for similarity. It's angle, 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 side, 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 angle, side. All right, those are the only 3 that can show similarity. All right, last one. It just wants to know which of these angle choices will not show similarity. So which of these stuff listed would not be enough to show similarity? So let's just go through it. So first off, we got to look at how the triangles are labeled so we can figure out where the corresponding sides are. So ABC, RST. So they said angle S is congruent to angle B. Is S and B corresponding based off of how they listed them? So don't base it off the triangles, base it off of how they name them. Because remember, you're supposed to name them based off of corresponding sides and angles. So are the B and S in the same spot in how they list? In other words, are they the second letter? Yes. So those two are corresponding, so they have to be congruent. What about C and T? Yes, they're corresponding, so they got to be congruent. So I got 2 congruent angles. Is that enough to prove similarity? Yes. Because remember, by the third angle theorem, that means A and R are going to be congruent as well. Now, the second choice, it has an angle, and then it's saying that 2 different proportions are proportional. So, angle R is congruent to angle T. Angle A is congruent to angle R. Are those corresponding angles? Yes or no? Is A and R corresponding angles? Yeah, because they're both listed first in how they labeled them. Now, AB over RS. So is AB and RS corresponding first off? So is AB and RS next to each other in the line of how they're labeled? Yeah. AB, RS. So they're corresponding, and says it's equal to AC over RT. So AC and RT, are those corresponding? Yes, because if you stay this backwards, A and C would go together, R and T would go together. Now, to double check, I'm going to actually put where those labelings are. So A is here, R is here, and then they also said AB, so this side, AC this side, RS this side, RT this side. Is that enough information, what I just marked, to prove similarity? Yes. By what postulate? So this is angle, angle. So what postulate is this one? It's the one we just did. Side, angle, side. Now, for time's sake, I can go ahead and tell you that this one's similar because of side, side, side. Now, this last one, they got RTAC, so these two. They got TSCB, so these two. And they got B is congruent to S. So, based off of where the red stuff is marked, can we prove similarity by that? Nope. Because if you look at where the angle is, it's not formed by the 2 corresponding sides. And so actually this one would be SSA, which, remember what I said, if you spell that backwards, I don't want those in my class. All right. So this one is the one that doesn't work. All right. So your assignment for today, there is a new Delta Math. It's just on this stuff. So similarity, really basic. It shouldn't take you very long. You only got about 10 minutes. I mean, you can start it. I prefer if you do. Or at least work on the one from yesterday, because I know some of you asked for help. Okay, come see me. But I want you guys to use this time and get to work. This is not a pack up time. I still expect you to work a little bit. That's fine. For unit 2 or unit 1? I don't have them in the folders yet. So I'll have to give it to you.
That's the way, that's like